In this video, we are going to answer one important question. Where in the world does this formula for the volume of a cone, pi r squared h over 3, come from? Hi everyone, this is Lando Assistant, and in this video, we are going to answer that question. Let's begin by situating our cone in an XYZ space where the vertex of the cone is at the point of origin. We are going to use a calculus method called the slicing method in order to derive the formula using definite integration. So let's label the axis. Let's call this as the x-axis. This is the y-axis, and the vertical axis is our z-axis. Then let's locate the center of the circular cone, and from the center, let's draw its radius, and let's label it as capital R. Then from the vertex, let's draw the height, and let's label it as capital H. Now, let's cut this cross section, a circular disc that is perpendicular to the vertical axis Z. And let's continue cutting this cone into circular disc like this. In fact, this cone can be looked at as the summation of all these circular discs that we can cut from the cone. And let's take a look at the property of one of those discs. So we have here a circular disc. Its shape is a cylinder. The radii of all the discs that can be cut from here are different because it will depend on its distance from the point of origin. The closer you are to the point of origin, the smaller is the radius. The closer you are to the circular base, the longer is the radius. And based on our notation here, that radius is our y, because y is our horizontal axis. Now, the thickness of this cylinder are theoretically so thin, and we call that as our infinitesimal dz. Then let's recall what is the formula for the volume of a cylinder. The volume of a cylinder is equal to pi r squared h. In here, our r is this radius y. So let's substitute y for r to have pi y squared dz as our representation for the volume of this circular disc that we sliced from this cone. Now our problem here is there are two variables. We have the variable y and we have the variable z. So let's represent this y in terms of z. Now going back to our cone here, notice that if I draw this line, then that line can represent the distance from the z-axis going to the line. And if you know what's the equation of this line, then we'll be able to have a representation for this radius. So what is the equation of this pink line? The two variables involved here are z and y. The equation is z equals the slope of this pink line, the rise is h, and the run is r. So h over r times y. And solving for y, we have y equals r over h z. And we can now replace this y by this expression. So y is now r over h z. So substituting now that value to y, we now have this equation. The volume of this circular disc now is pi times the radius squared times height, where the radius is r over h z, then we square it. The height of this thin disc is the infinitesimal dz. Notice now that this part here of the equation is the area of the circular base, and this dz is the height of this disc. So at this point, what we know is just the volume of one disc. And there are infinitely many discs that we can cut from this cone, and we would like to sum up the volumes of all those discs. And in order to sum up all those volumes, we need the concept in calculus, which is called as definite integration. So let's zoom out a little bit so we can have more space. So if this is the volume of one slice of a disc, the volume of the entire cone is now given by the integral from z equals 0 to z equals h, because the height is h, of this volume, pi times the quantity r over hz squared dz. What this means is we have here the expression representing the volume of this circular disc, and there are infinitely many circular discs that can be cut from this cone, but those discs are situated from z equals 0, which is our lower limit of integration, up to z equals the height itself of the cone. So what we need to do now is to solve this definite integration problem. We have here an exponent, so let's simplify this part to arrive at r squared over h squared times z squared and copy all the rest. Our variable of integration is z, so z is a variable here, but this part here, pi r squared over h squared, this is just a constant. So we can pull this out of the integration symbol, and this is now what we have the constant pi r squared over h squared times the integral from 0 to h of c squared dz. We need to find the antiderivative of c squared dz. And we can use this power rule of antidifferentiation. The antiderivative of x raised to n dx is equal to x raised to this exponent plus 1 over the same exponent n plus 1 plus a constant. Since we are doing definite integration here, we'll not be including this constant anymore. So we now have z raised to 2 plus 1, that is c cubed over 3, and we will evaluate that from 0 to h, and we just copy the constant outside the integration symbol. Then, evaluating this part here, we copy this constant pi r squared over h squared, then substitute h to z to have h cubed over 3 minus substitute 0 to z to get 0 cubed over 3. Then let's continue. This part here is just 0, so we only have this part, pi r squared over h squared times h cubed over 3. Now h cubed divided by h squared is equal to h, so this is h. So what's left is pi r squared h over 3. And generally, this capital R could be replaced by this small r, and this h can be replaced by this small h. And so, we now have the formula for the volume of the cone, and we derive this using the slicing method. And so, this is now the answer to our question at the beginning of this video. The formula, V equals pi r squared h over 3, is derived using calculus method, using the technique called definite integration. So thank you very much. This is Lando Assistant, and we hope to see you again in our next video.